Good morning to you all. Welcome back to class. Here are the objectives of today's lesson. Number 1. At the end of today's lesson, all the students should be able to state the 3 factors that affect preferential discharge of ions. Objective number 2. At the end of today's lesson, all the students should be able to name the apparatus used in the electrolysis of acidified water or dilute tetraosulfate 6 acid. Objective number 3 is that at the end of today's lesson, all the students in this class should be able to state the ions discharged at the cathode and at the anode. Objective number 4 is that at the end of today's lesson, every student in this class should be able to write the equation for the reaction at the cathode and at the anode. And the last objective, but not the least, is that at the end of today's lesson, all the students in this class should be able to describe and draw the diagram of the instruments used in the electrolysis of acidified water or dilute tetraosulfate 6 acid. So, welcome to class once again. So there are 3 factors that affect the preferential discharge of ions. The first one is the position of the ion in the electrochemical series. The second one is the nature of the electrode used. And the third one is the concentration of the ion in the electrolyte. So let's begin with the first one, which is the position of ion in the electrochemical series. Let's see how it affects preferential discharge of ion. So if you look at the diagram at the right hand side of this slide, you see cation and anion. And of course, the first ion you see at the cation side is K+. K+ means potassium ion. And the first ion you see at the anion side is F-. F- means fluoride ion. So let's say in an electrolysis where Na+, that's sodium ion, and H+, that's hydrogen ion, are the 2 cations that are formed by the electrolytes. And of course, being positively charged ions, the 2 of them will migrate to the negative electrode, which is the cathode. And of course, only one out of the 2 ions, sodium ion, hydrogen ion, will be discharged. So the factor now is we look at their position in the electrochemical series. So the one that is lower in the series will be the one that will be discharged. And of course, between Na+ and H+, which one is lower in the series? H+, of course. So H+ will be the one that will be discharged. I have used which factor now? Position of Na+ and H+ in the electrochemical series. And by the virtue of their position, H+ being the lowest one in the electrochemical series will be the one that will be discharged. And if it is for the anion, let's say in an electrolysis where Cl-, that is chloride ion, and OH-, that's hydroxyl ion, are the anions that are discharged in the electrolysis. And of course, the 2 of them will migrate to the positive electrode, which is the anode. But the one that is lower in the series than the other will be the one that will be discharged. So between Cl-, this is Cl-, and OH-, which one do you think will be discharged? Of course, OH- will be the one that will be discharged because it is lower in the series compared to Cl-. And that is what the position of ion the electrochemical series is saying, that the more electronegative an anion is, the less it is discharged, and the more electropositive a cation is, the less it is discharged. The nature of electrode used. So the nature of electrode used affects only the cations in the electrolysis. it does not have effect on the anions. And how does it work? The nature of the electrode used will be the determinant factor of the cation that will be discharged at the cathode. And so if electrodes that have affinity for one ion or the other in that particular electrolysis is used, it will interfere, and it will be the one that will decide on the type of cation that is going to be discharged without making reference to their position in the electrochemical series. But we have electrodes that will not interfere, that will not interfere on which cation is to be discharged, which one is not to be discharged. Those ones are called the inert electrodes. They are called inert electrodes, and we have examples of carbon electrode, or if you like, you call it graphite electrode. We have platinum, we have gold, we have rhodium, and etc. and etc. And so, but the commonly used electrode are, we have copper. Copper electrode is common, and the zinc electrode, lead, silver. We also have graphite. These ones are the commonly used electrode. The concentration of ion in the electrolyte. Concentration of ions affects only the anions. And don't forget that I told you that the nature of electrode affects only the cations. So, in an electrolysis where we have concentrated tetraoxophosic acid and water mixed together, so meaning that the concentration of H2SO4 is higher than concentration of water, and of course H2SO4 will dissociate to form SO4 2- as an anion, and H2O, which is water, will also dissociate to form OH-, that's hydroxide ion, as an anion. So the two anions that are formed in this particular electrolysis we are talking about are SO4 2-, that's tetraoxophosic ion, and OH-. So, but in the electrochemical series, the two of them are far apart from each other. This is OH- and this is SO4 2-. So because the two of them are far apart from each other on the electrochemical series, therefore we cannot use their concentration again. So what we are going to do is that we will then go back and use the first factor, which is what? Position of ion in the electrochemical series. And of course, the one that is lower in the series will be the one that will be discharged. But if it is in a situation whereby the anions that are formed are close to each other, let's say I- and OH- are the anions that are formed and have migrated to the anode. So I-, if I-, the compound that produces I- is more concentrated than H2O that produces OH-. Therefore, I- will be the one that will be discharged, because the compound that produces I- is more concentrated than H2O that produces OH-. So what the concentration rather of ion in the electrolyte is saying is that when the two anions in questions are close to each other, then we can consider their concentration. But when the two anions that are competing are not close to each other, concentration will not have effect in such electrolysis to determine the anion that is going to be discharged at the anode. So this is the summary of what we are saying about these three factors. Of course, you can see that the position of ion in the electrochemical series affects both the anion and the cation. It affects both of them. You can see I put XX showing that it affects both of them. But the nature of electrode, you can see the column of anion is empty, but the column of cation is marked. So nature of electrode affects only cation. It doesn't have any effect on the anion. And of course, concentration affects only the anion, no effect on the cation. So this is a summary of what we are saying about those three factors. Electrolysis of acidified water, or if you like, you call it electrolysis of dilute tetrahydrophosic acid. The apparatus used in the electrolysis of acidified water or electrolysis of dilute tetrahydrophosic acid is Hofmann photometer. Hofmann photometer is what you see here at the right hand side of the slide. So water is a poor conductor, and then few drops of tetrahydrophosic acid will be added to the water, and then to catalyze or to improve its conductivity. So that's why it can be referred to as electrolysis of dilute tetrahydrophosic acid or electrolysis of acidified water, not just ordinary water. So if you call it electrolysis of acidified water or you call it electrolysis of dilute tetrahydrophosic acid, you are saying the same thing. But how does it work? The mixture of H2SO4 and H2O will be poured at the middle opening here, and then the opening down here will be sealed with either graphite anode, graphite cathode, or platinum anode, platinum cathode, and will be connected through wire to a power source. And then that is how the process will just keep going. Yes, the electrode used in Hofmann photometer are platinum anode, platinum cathode, or graphite anode, graphite cathode. But how does it work? H2SO4 will produce hydrogen ion as a cation, SO4 2- as an anion, and H2O will produce hydrogen ion as a cation, OH- as an anion. But OH- is lower in the series, in the electrochemical series, compared to SO4 2-, and because of this, OH- will be the one that will be discharged, and through OH-, which is hydroxide ion, oxygen gas will be liberated at the anode, while hydrogen ion, being the only cation form in that electrolysis, will migrate to the cathode and will be discharged there, and it will also liberate hydrogen gas. So the function of Hofmann photometer is to determine the volume ratio of hydrogen to oxygen in the electrolysis of acidified water or electrolysis of dilute tetrahydrophosic acid. So as you can see, these are the two compounds that form the electrolytes. We have the H2SO4 and we have the H2O. This is H2SO4 and this is H2O. H2SO4 produces H+, 2H+ as the cation, while H2SO4 produces SO4 2- as the anion. H2O produces H+ as the cation and OH- as the anion. So concentration now, because the concentration of H2SO4 will be higher than that of H2O, so we say the ions produced by H2SO4 are more concentrated than the ions produced by H2O, and therefore, what about their position? OH- is less electronegative in the series than SO2 SO4 2 minus, I beg your pardon. But for the cations, we have hydrogen ion, of course, is the same thing. Reaction at cathode. All the hydrogen ion present in this electrolysis will all migrate to the cathode, and they will then begin to gain one electron. All of them will begin to gain one electron. So this is hydrogen ion gaining one electron here, and then forming hydrogen, neutral hydrogen atom. So this hydrogen is neutral, it doesn't carry any charge. And so because this hydrogen gain one electron to form hydrogen, this neutral hydrogen atom, that process is what we refer to as a reduction reaction. Gaining of electron is what we call reduction reaction. So but hydrogen cannot be written like this in any chemical reaction because it is diatomic in nature. So two of these neutral hydrogen atoms will be combined together to form a diatomic hydrogen, which is H2 here. Reaction at cathode. So the two anions that are formed in this electrolysis will migrate to the anode. I'm talking about SO4 2 minus tetrasulfide ion and OH minus hydroxide ion. The two of them will migrate to the anode, but because OH minus is lower in the series than SO4 2 minus, OH minus is less electronegative compared to SO4 2 minus. Therefore, OH minus will be the one that will be discharged. And then, by the time OH minus is discharged at the anode, what will happen is that it will lose an electron to form OH group. OH minus will lose, this is OH minus, it will lose an electron and then form OH group. So the process of losing electron is what we refer to as oxidation. So oxidation is loss of electron. So OH minus will lose an electron to form OH group. OH group cannot stand alone. OH group is just like a parasite, especially in organic chemistry. So two OH group will be combined together to form H2O and O, and of course oxygen is not written as O in any chemical reaction because it's also diatomic, just like hydrogen. So 2O will be combined together, two oxygen atoms. This is oxygen atom, this is oxygen atom, will be combined together to form a diatomic molecule, which is O2 that you see here. So this is a reaction that occur at the anode. Overall reaction. Overall reaction is the combination of the reaction that occur at the anode and the reaction that occur at the cathode. The reaction that occur at the anode is referred to as anodic half reaction, and the reaction that occur at the cathode is the one that is referred to as cathodic half reaction. So what happened is that the two reactions combined together make up a single reaction. That's why they are called half and half. And you know, when you add two half together, you are going to get one. So I told you earlier that hydroxide ion is the one that is discharged at the anode, and it produces a molecule of water and oxygen gas by losing one electron. And at the cathode, hydrogen ion is the one that is discharged, and it gained 1 mole of electron to form hydrogen gas. So but the number of atoms of each element at the product side and at the reactant side must be the same. So for the anodic reaction, we have 1 oxygen at the the reactant side, 3 oxygen at the product side, 2 hydrogen at the product, 1 hydrogen at the reactant side. That is not the same. So what do? 1 hydroxide ion loses 1 electron. So if I make this 4, that means 4 hydroxide ion will lose 4 electrons. And then I just add 2 to this. So these 2 will take care of both the hydrogen and the oxygen. So if I put 2 here, that 2 you multiply by the 2 that is sitting beside the hydrogen. That means I have 2 times 2, 4 hydrogen, which is the same thing as the number of hydrogen that I have at the reactant side. So I have this, because this 2 is meant for hydrogen and oxygen, that means I have 2 oxygen atoms here and I have 2 oxygen atoms here. The 2 combine together making 4, which is the same with the number of oxygen that I have at the reactant side. So this equation is then balanced. For the cathode, 1 mole of hydrogen ion gain 1 mole of electron to form hydrogen gas. So if I make it 4, if 1 gained 1 electron, 4 will gain how many electrons? 4 electrons. And then I decide to put 2 here to ensure that the number of hydrogen atoms that I have here is the same with the number of hydrogen atoms that I have at the reactant side. So the number of electron gain must be equal to the number of electron loss. That is the rule. So, and once they are equal, that means you can cancel the 2 of them. So they cancel each other. And then to get the overall reaction, what you need to do is add what you have at the reactant side of cathode and what you have at the reactant side of anode together, and then add what you have at the product side of cathode and what you have at the product side of anode together. So at the cathode, I have 4H plus as my reactant, and that's what I have here. At the anode, I have 4OH minus as the reactant, and that's what I have here. And then these are the only 2 reactants, and then I put the arrow that separates the reactant and the product from each other. So I have 2H2 as product from cathode, and that's what I have here. I have this O2 as product from anode, and that's what I have here. I have 2H2O as product from anode, and that's what I have here. And then this is the overall equation of the reaction that occur at the anode and at the cathode. So the 2 of them combined together have already given us a single equation that we refer to as overall equation. What have we learned in today's lesson? 1. We can state the factors affecting preferential discharge of ions. 2. We can now name the instrument used for the electrolysis of acidified water or dilute tetrasulfate 6 acid. And the 3rd lesson is that we can now state the ions discharged at the cathode and at the anode. Number 4, we can write the equation for the reaction at the cathode and at the anode. And the last lesson is that as from now, all of us here can now describe and draw the diagram of the instrument used for the electrolysis of acidified water or dilute tetrasulfate 6 acid. That is all for today. My name is Ibukunolu Ademola, and here is my email address for your comments or question. Bye for now.